Hi, I'm Andrew, and this is part 9 in the Advent of Code series, where every day I attempt to solve a new code challenge. The previous videos are on my channel in a playlist called Advent of Code 2022, and if I'm able to solve any challenge, the code that I write, I'll update to a public repo, and the link for that is in the description of this video. But let's get started for today. For day 9, it is the rope bridge. This rope bridge creaks as you walk along it. You aren't sure how old it is or whether it can even support your weight. It seems to support the elves just fine though. The bridge spans a gorge which was carved out by the massive river far below you. You step carefully, and when you do, the ropes stretch and twist. We decide to distract ourselves by modeling rope physics. Maybe you can even figure out where not to step. So consider a rope with a knot at each end. These knots mark the head and the tail of the rope. If the head moves far enough away from the tail is pulled towards the head. So due to nebulous reasoning involving plank lengths, you should be able to model the positions of the knots on a two-dimensional grid. Then, by following a hypothetical series of motions, which is our puzzle input, we can determine how the tail will move from the head. So due to the plank lengths, the rope must be quite short. In fact, the head and tail must always be touching. Diagonally adjacent and even overlapping both count as touching. Okay, if the head is ever 2 steps directly up, down, left, or right from the tail must also move 1 step in that direction so it remains close enough. Alright, so here we've got the tail and the head next to each other, like this. Okay. So in this case, when the head moves to the right, then the tail also moves along. And here, if the head goes down, then the tail follows. If the head and tail aren't touching and aren't in the same row or column, the tail always moves 1 step diagonally to keep up. So here, the head moves up 1, but they're diagonal. The head moves up 1, then the tail jumps up to the top right, and vice versa. So if the head moves to the right, the tail jumps up. So we need to work out where the tail goes as the head follows a series of motions. Okay, so at each point we just need to calculate when the head moves, where does the tail end up. So we're going to have this list of instructions for the head to move, and it's right, up, left, and down, and how many. So what happens here, this is the initial state, and we're going to move right 4. And so this is the initial state, the head is covering the tail. Okay, and this is each step. So the first step, the head moves 1 to the right, and then another one, and another one. Okay, and S, that might just be, the starting position. And then when it moves up 4, so we could just see this is how things go. And here, the tail was to the left, but when we move up, it's still connected, so it doesn't have to move, but then when the head goes up again, then the tail jumps diagonally. Okay, so this is just visualizing the rules that it already showed. So after we simulate the rope, we need to count up all of the positions the tail visited at least once. So we just need to mark if the tail ever visited that position, and if it did, we need to add up how many. Okay, so this is another problem where we'll have to create a grid and just sort of maybe have a state machine where we can update with the moves. Let's take a look at the puzzle input and get started. For parsing, this won't be too complicated because it looks like we just need to calculate the direction and then the quantity of steps in that direction. So let's get started. There's 2,000 steps. So the first thing that we're going to do is process the inputs. I'm just going to make them as movements. And we're going to have the direction, and that can be, we'll probably have the direction enum, and we'll have a amount, which is just a number. So then we will make this a direction class. We're going to have up, down, left, and right. Okay. And we'll just want to make a way to process each line into a direction, so we could do that even, or a movement. So we could probably have something like this, where we would say it's going to be of a string, and then we will return a movement from that. So we'll say creating a movement will be direct. We'll make a value for direction. Actually, we're going to want to split the line first. So for each line, I think there's just a space in between that we can count. So we'll do a destructured declaration there, which will be direction, code, and amount. And that will be like this, string split by a space. And then for this, we'll say when the direction code is the direction code is up. And are they uppercase? No, they're just a letter. So when it is U, we would say it is up. Direction up. And fill in the rest of these. And for this one, we'll just put the else case as right. So then for our movement, we can just assign directly the direction and the amount. But amount needs to be converted into an integer. So there we go. We're going to map these out as our first step. So movements is going to be input input map, and each line we will map a movement of, oh, this needs to be in a companion object so that we can access it statically. Like this. Oh, we'll just do that. Okay, so now we can say of line. And we will set a breakpoint and just check that these all processed fine. And we don't. So then we'll set a breakpoint here and just make sure that our mapping was working correctly. So then we'll set a breakpoint here and just debug to make sure that our mapping worked correctly. We should have a list of all our movements, and they're in this format. So now we can work with that. And I'm going to increase the font size. Forgot to do that already. There we go, so it's a little easier to read. And for the steps, I think we don't really need to reference these, so I'm going to close that file. What we don't get is what the grid is going to look like, so I think we'll just have to assume that we always start in the bottom left. I don't remember reading that, but anytime we move in a new direction, we'll just have to account for that, because it's probably possible for us to go, outside of this. I'm not sure. I'm gonna double check to see if it says. I think we can't really assume that it will always start in the bottom left, so we'll just have to account for that. But what we will need to do is just make a grid, which would be a 2D array. So we'll say our grid is a list of lists, and inside of each list, I think we just need to have a Boolean. Yeah, I'm not sure what we would need to model here, because at the end, all we need to track is where the tail visited. So as we go through the program, we're just going to keep track of where the head is, and then after each step for the direction, we'll move the head to a new point and then calculate where on the grid the tail ended up. So we might be able to get away with just this. Actually, I think what we can do is just model this out. We don't even really need lists. We just need relative positions. So we could really store maybe just a list of all positions that the head and the tail have moved to. So I'm going to create a grid class and let that kind of handle updating these. So there will be a list of head positions, and that will be a mutable list of a pair of integers, and that's just going to be the coordinates. And in fact, I'll make a coordinate class just for easy x and y positions. Coordinate. and that's going to have an X and a Y. So then we'll just do this. So the head position and the tail position will each need to have a list, and this will just track where all it's been, and when we're getting our logic at the end, it will just go through and filter out duplicates from this. Okay, so for these, I think they should both start with a 0, 0. So we'll just do that. Coordinates, and it will be 0x and 0y. And then, so each time a movement occurs, we will just, if it's right or left, we'll just apply an operation to the last coordinate in the list for the head. So the head should just be kind of a static behavior, but then the tail, for it to move, that's where we'll have to calculate some things like diagonals. Okay, so we will create a new grid. And then really just take our movements for each, and grid will need a move head position or a move head function with the movement. So we'll create that on top of it. Grid. We'll put that here. Oh, movement. It already has a type. So there we go. Put that down below the member variables. So then based on where we move the head, what the movement is, we'll do different things. So when movement, and we can, since we have an enum, we can just fill that out. Let's see, when movement, oh, when the movement direction, that's what we need. When the movement direction is each option, we can fill it. We'll do different things on to the head. So let's just take a look at what each thing could do. So if we're moving up, we would say head positions, add. Well, first we're going to take the current position, right? So we'll take head positions last. That's going to be the most recent position it was in. And we're going to use that as a scope for this and say head positions, we're going to add a new coordinate, and we're going to take current position, and we're just going to say current position. Let's see, current position. If we're moving up, then the y is going to go up. So coordinates, we'll say the current position x and the current position y plus the movement amount. Okay. And we'll just kind of copy this and modify it for each direction. So if we're going down, it's going to be minus the amount. And if we're going left, then it will be the x-axis instead. So x, if we're going left, it's going to be minus the amount. And if we're going right, it would be positive. Okay, so we'll do this. and just add the amount. So then once we're done processing all of the movements, we should have the head positions and kind of see the path and look at the path that it went in. We have head positions, and so then tail positions is what we'll have to do after each of the head movements to see if it needs to change. All right. So let's debug that and see what the head positions look like. Okay, so if we look at the grid, we can see head positions. There's 2001 because we started with our initial state. And then we could see, so here it looks like it went left 2. I guess I should pull back up the sample input. So the very first move we make, is down 2, and that's because we're looking at the y. So y goes down 2, and it goes to the right 1. Then it goes to the left 2, so then we're negative. So it looks like it's following along pretty well. Now we need to just model what the tail position does to follow. Okay, and so that will be in here. We'll say we could just have one, because it doesn't matter really what direction the head is going. We should always just have the same logic for the tail to move. So we'll do that. Move tail. That's a private function. And that is going to just be called at the end of this function every time. So we'll move the tail. And it may or may not need to move, right? Because if it's still touching diagonally, then we don't need to move anything. So let's see what that would look like. We will need to get whether they're touching to see if it even needs to move. So we could just copy this and say head position is going to be this value, and actually we'll just make a couple variables here so it's simpler. So the head position is the last item there, and the tail position is the last of the tail positions. Okay, and we're going to say what would we do here? I'm going to look back at the examples. So in the first case, they are at the same position. So we wouldn't do anything with the tail. In the second example, the head is 1 to the right. So we could check if either the x or the y are the same and the other is only 1 different, we don't have to do anything. So let's do that. If head position x is the same as tail position x and head position y is only 1 difference, so head position y minus tail position y. I think if we get the absolute value of that is less than or equal to 1. Let's see, we'll go absolute. then we shouldn't have to do anything. And that will also count if they're on the same space. So it handles if they're on the same space or if they're touching the same left or right or up or down. Would that also count for vertical or diagonal? No. So maybe we should count each way if they're as long as they're both within one difference. So that would be kind of the same here. So as long as their y values are within one and either mix, we shouldn't have an operation. So let's see what else. Otherwise, we know that there will be. So in this case, the tail has to move over one to the right. So I think we could just do an else and handle all the cases here. So we would first want to check if we're moving just vertical or horizontally. So in order to check that, if head position Y and tail position Y are the same, or if the X values are the same, then we know we are not going diagonally. Then we just need to figure out which one we are doing, and we'd probably want to separate these out so we could just do the logic here instead of having to recheck which way we're going. So yeah, let's do that. We'll say here, if the X values are the same and the Y values are different, that means we're going a vertical move. Otherwise, if the Y values are the same, then we know we're doing a horizontal move. Otherwise, we would know that it's a diagonal move. Okay, and we could probably just figure out from here. So if we know we're going vertically, then we would want to figure out where the tail position should go to. We need to know if it's going to be above or below the head. And in order to know that, we would just need to know maybe the difference. So if for example, if the tail is at -1 and the head is at -3, then the tail would need to move to -2. So I think we can take whatever the head's position is and subtract the tail's position. So if we take one away, would that work? Maybe not. Or we could take the absolute. So we could take the absolute value. So it'd be 3 minus 1 is 1. Or I'm sorry, 3 minus 1 is 2. We just need to find if it's above or below. So we do that with more branching if checks. Yeah, we could just do that. So if the head position of Y is greater than the tail position Y, that means that we would want to move the tail position Y just below the head position. So tail positions, that needs to modify our list up here. So we're going to go to tail positions. We're going to add a coordinate where the we're going to take the current tail position x, and for y we're going to take the head position y minus 1. Otherwise we will do it plus 1. I could probably do some clever logic here to just calculate this on the fly, but I kind of like breaking all these steps out, especially when I'm working on my solution, so that if anything's not working, it's just really easy to debug kind of what the step was. So for this, I'm just going to flip these values, and I think we would do the same thing here with the x values. Oh, and this should be the tail position. Swap the head positions with x. So then the last part of this to iron out is how we would make a diagonal move. So we already know at this point that we need to make a diagonal move because the head and tail aren't touching each other at all. So then the question is, to what degree, like what position we need to move from. Let's see if it gives us some examples here of diagonals. Okay, so if we're diagonal here where the head is up and over 1 to the right, if the head moves up 1, then the tail snaps up to be under it. But when it's horizontal, we got the same scenario here where it's up and over to 1 and it moves left 1, then the tail ends up going to the right of it. So we would just need to figure out the math for that, or we would need to figure out the check for that. So when we do have something like this where the head moves to where it's no longer touching diagonally, one of the distances will be 1 and one will be 2. So we just need to figure out which one that is. So x difference is going to be the absolute value of head position x minus tail position x. Then we'll duplicate that for y. And now whenever we run this, it should always end up being 1 is 1 and 1 is 2. So yeah, let's debug this and see. Just put a value there. Okay. We'll also get to check that everything else is running correctly. So there we can see it. The first time that we hit this, that's good to see because we should only hit this when we are in a case of a diagonal move, and here we have them like that. So it looks like the head is at 1, -3, and the tail is at 0, -1. So it was probably at 1, -2, which would have still been diagonally touching. So if we go again here, here we have a y diff of 3. We shouldn't have that. So I'm curious how it got into that state. The logic correct here. So if we're moving up, it'd be the y plus. If we're moving down, it'd be the y minus. If we're moving left, it'd be the x minus. If we're moving right, it'd be the x plus. So that all looks right, but maybe something's not catching here. Oh, probably, yeah, that makes sense. We aren't updating the tail position here, so it's going to get more and more out of whack the further we go. So I think so far we could just keep going with this. So if xdiff is 2, then we need to move left or right of head. Otherwise, we would move up or down. Okay. Yeah, and I wonder if the absolute value is good to use here. So, we can just check which is greater. We've been doing that the same in these other positions. So this would be really just the same logic here. So we could maybe even have a function under each of these for moving vertical or horizontal, and then in the diagonal we could just pass that same function across. I think that's what I'll do. Move vertical and move horizontal. Okay, we'll do that. And do the same thing here. And then I think our logic would still work, so move horizontal and move vertical. But I should rename these that we're moving the tail. Oh, I guess it doesn't matter because we're already inside of move tail. These are just local functions. Okay. Yeah, let's run it and just take a look at what the grid positions end up as. So inside the grid, tail positions are much less, but that makes sense because the tail only needs to move in certain conditions, whereas the head is always going to move. Let me zip these together and see. So head positions zipped with tail positions. So when we look at that, they both start out at 0. The head moves down 2, and then the tail follows. And then the head moves away again to the left or to the right, and then the tail moves up with it, right beside it to the left. So I think that makes sense. I'm going to validate with the example input because it'll be a little easier to walk through it. But so far, it looks promising. Okay, I think this was our example input. And I'm going to just put the group for testing. We'll do the grid head positions zipped with the tail positions. And then we can just debug that right away. Okay, so looking at this, there's only two. That doesn't seem right. Head positions, oh, there's only two tail positions. That also can't be right. So let's see what they do. The first movement is the default position, and then the second is going right 4. So when we go right 4, oh, you know what? We need to check each step along the way. So for the quantity, yeah, that's a good catch. We don't want to just jump the head 4 over, and we need to make each step along the way. So for that, the amount, when we take the amount, we're going to want to go an iteration here. So we'll say movement amount. We're going to repeat that many times. And then we won't need to add the amount. We'll just add 1 each time. Yeah, and I think that'll make sense. Yeah, and in order for us to zip them together better, I'm just going to add kind of the same position each time under here, just whether we need it or not. Tail position, we're just going to add the last one again. Okay. Then we should at least always have an even number of positions, even though the tail will have most of them duplicated. There we go, so size 9. So this is what it looks like. The first time the head moves, the tail doesn't move. But then when the head moves again, it moves up 1. Not sure why the tail is jumping so far over with the Y, so that could be a problem. Because what it should do is move to the right. The head should move to the right one. It should move to the right another one, and on the second step, the tail should just go to the left of it. But it almost seems like the tail is jumping to the right of the head. Yeah, I guess I'll debug that again and just validate. Yeah, and it went with the Y instead. So after this point, the tail isn't moving again at all. So something's wrong. Okay. Um, so if the head position, this might not be accounting for both going up and down, like into the negatives. Yeah, I guess I'll just set some breakpoints here just to see at each step what we're doing. Okay, so the first movement, that makes sense because the Y position are still, oh, that's what is wrong here. This is checking. Of course, I duplicated this without modifying them, so these should be X and Y, not just checking Y. All right, simple mistake, but a big bug. Now let's look. First time should be a no op, and then we should be moving horizontally. And we are. Okay, I'm gonna remove these and just check at the end what our grid looks like. So this looks a lot better. When the X is over to 2, then the tail moves over 1. Let's run some logic here just to count the tail positions, how many distinct positions there were. 10. What was the answer? So there's 13 positions. It says the tail visited at least once, so something isn't quite right. Yeah, and I wonder what it is. Here, I'm going to copy over this real quick, and I'll just compare it against what I have. I'll put it in there. So we started in position 0, 0, then we went to 1, 0, 2, 0, and 3, 0. Then we went to 3, 1, but we should have gone to 4, 1. Right. So that's in my diagonal logic. Something's wrong. I'm only moving up to it, but not over to its other axis. Yep. So, and that makes sense. Okay. So I think in this case, I will need to first set the tail position to the tail position Y to the head position Y. One is something I can change, the other isn't. Yeah, okay. Maybe I can't share this logic as easily. That's fine. For now, I'm just going to copy this out. Yeah, I don't really want to. Maybe I should make a way to edit these, but yeah, I will do that. I'll just reassign these. So the tail position is just going to be equal to the tail position. Copy. Actually, I don't even know if it matters. Yeah, we'll do that. Where we're going to copy over The X, well, in this case, we're moving left and right, so we want to copy the Y. Something like that. And then here we'll do the same thing for the X, and that's just going to make it when we move horizontally, we're going to move up to what it should be or down. Try that again. Oh, right, we got out of bounds. Yeah, I wonder why that would be an issue now. And that's because this is our input. This shouldn't be there, right? Okay, so I'm going to put this back in and we can just look through at the group. I was going to evaluate the expression to see, again, just the distinct values. So we'll do the grid, tail positions, distinct, and then look out over here. So now we do have 13 values, and that should be explaining why. So when we're here diagonally making the jump for the tail from the bottom row up, it also moves its x over 1. Okay, so I think we're good. I think we can just run with our real data. Should have an answer. I'm going to return that now. Just the grids, tail positions, distinct, size. So we have 6,284. Check that answer. And we got the right answer. So great. Let's move on to part 2. And now a rope snaps. So suddenly the river is getting a lot closer than you remember. The bridge is still there, but some of the ropes that broke are now whipping towards you as you fall through the air. The ropes are moving too quickly to grab, and you only have a few seconds to choose how you're going to avoid getting hit. Fortunately, our simulation can be extended to support longer ropes. Rather than 2 knots, you now must simulate a rope consisting of 10 knots. 1 knot is still the head of the rope and moves according to the series of motions. Each knot further down the rope follows the knot in front of it using the same rules as before. So yeah, now it's like a snake here. So when the head moves up from the first row, the 1 goes above it, which would make the 2 go up and diagonal, and the rest all follow, and then 5 is left. And then they all just kind of follow along. Okay, so what do we need to calculate? We need to keep track of the positions of the new tail, which is the 9th. In this example, the tail never moves. Okay. More types of motion are possible than before, so you might want to visually compare your simulated rope to the one above. More types of motion. I'm not sure what that means. Right, up, left, and down. Yeah, I don't really see any significant change. Okay. So now we just have to have these positions. Yeah, that's okay. We might just have to have a list of lists. And instead of taking the head and the tail, we would take the one in front of the other. I'm going to play around with that. Not positions. It's going to be a mutable list of, let's see, mutable list of a mutable list of coordinates. Okay. How do we know how many knots there are? Does it specifically say there will be 10? Yeah, I think it does. Okay. Yeah, is there a way to fill this with 10 values? Instead of making a mutable list of, we'll just create a new mutable list. Size is 10, and we're going to initialize it with, yeah, with just empty coordinates. Okay, it should be a mutable list of coordinates, like this. Okay, now we can get rid of all that type code. Get rid of these. So now we've got 10 knots, and then, yeah, instead of checking these, we'll just have to iterate over and kind of set each pair. And that's probably what we'll do actually, is just window this, yeah, we'll just window that. So whenever we want to move the head, this is what we'll do. Because like each pair, so the first and second, the second and third, they'll always act as like their own head and tail. So say not positions windowed to. Oh, what is this? Do we need to iterate over these? Okay. Okay, so we still need to start with the amount of the movement. So this will actually go inside, I think, like that. It's just that these will come in here. And when we're moving the tail, that will be given what its tail is. So it's going to have, right, we're going to have these, and we'll say val, yeah, I think that's going to be backwards. So the first one will always be the head, and the second one will always be the tail. We need to destructure them up here, like that. And we will need to pass the tail in so that it knows which of these lists to use. Right. And for head, that's just what we'll do. We'll set these as the lists. Let's reuse the name. Okay, I think everything else will behave pretty much the same. The difference being, let's see, tail positions, okay. We're going to do that, and then head positions, we just need to know the current head position. Okay, and that's a single coordinate like this. Okay, that way we don't have to rewrite too much. Okay. So far so good. Tail positions. That's because we need to take head positions last. So that gives us what we need. And then up here, I think is the only big issue. Grid. Not positions last will be our tail positions. So like that. Okay, and I want to make sure that it works for both part 1 and 2. The only difference here is the size of how many knots there are. So grid, I think, can just take that as a value and initialize it based on that. So not count. We'll put it like this. So when we create the class up here, we just need to pass 2 for that. And in part 2, we'll pass 10. Yeah, I think that's really the only difference. But let's rerun it for part 1 and just double check. It's going to give us an answer because we already have part 2, but 6284 is what we should have had. And we still have 6284. But the answer is the same for part 2, even though we have a different amount of knots. So I wonder what the deal is here. Yeah. Let's take a look at each change to the knot positions when I debug this. So, this is still for part 1. So that's okay. I'm going to sort of just disable this for now because I'm only caring about part 2 logic. But when I upload my code, it'll be sharing that same function. Okay, so knot positions. When I do this, there's only 2. And that's because I still have the grid being initialized, so let's just do this. Now for part 2, I should have 10. And I do. So let's see what kind of changes as it goes along. They each have an empty coordinate, or an empty list of coordinates. Once we go the second pass, what do we have? They still each only have 1. Yeah, okay, so as we go along, So the first knot, which is at the very head of the chain, has moved once, but the one next to it hasn't, which makes sense. And let's just see how it goes. If we just keep running through. Okay, so that's all the times that it went down. And I think that's probably our problem, is that it's applying this down to each knot and tail pair, which probably isn't what we want, right? Yeah, because the tail would be staying the same, but it should not completely follow. So these are all the same. So yeah, so I think something's wrong with the logic there. Okay. So what I actually need to do is take the movements. I'm applying the movement commands to each head down the window chain, but actually the movement command only applies to the head, like the very first item in this list, this first knot. And then every other one underneath is going to be moving, it's going to be acting as a tail. So I only need to, instead of doing the movement like this each time, I think it just needs to happen like this, where the very first knot position gets these applied, and then the rest will follow suit using their positions. I still need to window them, but I think this logic just needed to be lifted up. So now I just need to take the last knot position. So that would be knot positions. I think the first item. We could say is head positions, like that. Okay, I'm gonna rerun it, and I think this will probably make a little more sense. I'm gonna do it the sample input again, just to kind of verify this. I think it was these instructions. So I'm going to run it with the new kind of movement behavior and just see how things look. I'm going to set a breakpoint. Yeah, I think here, because we can still see all the positions. I don't need to breakpoint there, and I don't need to, oh, here it is. So under the grid, the knot positions, they're each going to have one move per instruction, so this one will always change, but this one only moves once the head gets far enough away. This one kind of stays, so it stays at the 0 for 3 spots. This one stays there for 4. So this one, at the end, we can even see that it just never moves. But the other one above it doesn't. And what does it look like in the grid? The last one to actually move from 0 is 6. So that would be, so head counts as 1. Yeah, let's see. I think the last few wouldn't even move. In fact, I can just map these to distinct to see. Yeah, so if I look at this, these last three, they don't move at all. And then these two just move kind of one away. And I think that looks right. You know, looking at this 5, that only ever gets here. So yeah, I'm gonna just try that for our output. I can put this back. Okay, yeah, so 13 and 1, that's what would be our answer for the sample data. For the real data, let's just run it. 2,639, it says. Let's check it down here. And that is not the right answer, it's too low. Okay. But I think it's still working for the first question. Just to make sure. 6284. I'm doing 6284, so it works on the smaller data set. It would be good to know what changes here. Let's see, one of the only things I can think of is there's this messy check here. I was originally assuming that it would only ever be one of these is 1 and the other one's 2 for a diagonal jump, but it seems like there's a different case where sort of somewhere along the chain one of the knots can kind of whip even further out. So maybe it's just because 1 is the default, or I guess only 1 is being checked explicitly and the other one is always catching on the other one. So maybe I just need to check here if the diff is greater than the y diff instead of if 1 is, you know, yeah, let's rerun that because I could just be really close. So 6284 would still be the correct answer, I think, for the first part, 6284, but the new output for part 2 is 2640, which I think was only off by like a couple. Let's try that. Okay, still not the right answer. The only other thing that I didn't consider was if the x and y diff could be the same. If I'm checking greater than or equal, if they're ever the same, then it's going to be kind of off by 1. So let's take a look and see if they could be the same, because the instructions show that there's new movements now, which means that the head could actually go diagonally, and then the tail would have to follow it diagonally. I don't know if it shows any examples like that, but I'm just going to check just to see if it makes a difference, right? Because if an item moves like up to the 1, up and right 2, the tail of that should probably just move up into the right 1. So I'm gonna just set something here and see if that's something that I should account for. Yeah, okay, so here we've got some scenarios where the diff is the same. Yeah, so this is 2 below and 2 to the right. So maybe that's all that I need to add is if they are like that. So we'll say if they're the same, actually we'll add this as the else case. So if x is greater than y, else if y is greater than x, else we know that they're the same. So what would we do if they're the same? We would just move it, I guess, the difference. Yeah. We'll just make a move diagonal. And what is that going to do? That's going to check some numbers. So yeah, I guess we'll just figure it out. If the x of head is greater than the tail x, we're moving right. If the head position x is less than the tail position of x, then we're moving left. And then we're doing the same for y to check if we're going up and down. So if the head is above this one, we're moving up. And otherwise, moving down. Okay. Yeah, I guess we'll just set our offsets like this. I think we're only ever going to move diagonally up into the left, right, down into the left, right, 1. So let's just set these for each way. So if we're moving right, then x offset is going to be 1. Here it's going to be -1. And then here, same thing for y. Yeah. And then we'll basically just update the tail's position. Yeah, coordinates, we'll take that, and we'll just take tail position plus, we'll take the tail position's x plus the x offset, and the tail's y position plus the y offset. Yeah, I wonder what that'll do differently. That shouldn't ever happen for part 1. So let's rerun. I'll rerun part 1, make sure that it's still working for that. 6284, that was it. 2661 is our new answer for part 2. Let's check that. Awesome, that was it. So very small detail. It wasn't super clear, I don't think, in the instructions that would be the case. Well, actually, I guess it was here. It shows, yeah, it shows that we could move or diagonally 1. So yeah, that's just all I should have noticed. But yeah, looks good. I'll be back tomorrow with a new video. Thanks.